Hi guys, today the hi guys. Today the video that you're going to watch is all about error checking in computer communication. So let's get right to it. There's three main forms of error checking that we need to consider, that you need to know about for the HSC. These are parity checking, checksum, and cyclic redundancy check. Now we're going to look at each of these in turn. Parity checking, when communications via modems was just starting out, so back in the late 70s, the early 80s and so on, data was sent over the computer as it was typed. So when you press the letter A, the data related to the letter A, so the code, will be sent to the other computer, the receiving computer, straight away. The packets look a little bit like the diagram below. So we've got our start bit, we've got our ASCII character letter A, we've got our parity bit, and we've got our stop bit. And as you can see, the data packet is about 10 characters long. The two computers that were in communication would agree upon either having even or odd parity. It didn't matter which one, as long as they both had the same. So we've got a couple of computers. One of them says to the other, let's have odd parity, and the other one agrees. Then they would check each machine would check the incoming packet to see if it followed the parity rule of being odd, which is the case for this communication. They ignored the start and stop bit and just made their calculation based on the 7-bit ASCII code and the parity bit itself. So let's take a look at that. So here comes an incoming packet of data, 10 bits. The computer knows that this data should be odd. It ignores the start and the stop bits, and that leaves it with 1 1, 5 zeros, and a 1. You can see those from here. The computer adds the ones, and that makes 3. 1 plus 1 plus 1. It determines that 3 is an odd number, so it thinks that the data being sent is correct. And indeed, we know that it is, because it was the capital letter A. Sometimes, however, corruptions occurred. So the data would come in. As you can see, we have a corrupted bit. The computer thinks this data should be odd. It ignores the start and the stop bits. It leaves it with 1 1 0 1 0 0 0 1. It adds the ones together. That makes 4. 1 2 3 4. That's an even number. So it's expecting odd, it's getting even, so this data is incorrect, and the computer asks for a retransmit of that packet of data. Sometimes, however, it used to go horribly wrong. So in comes our data. You can see this time that 2 bits have been corrupted. The data should be odd. It ignores the start and the stop bits. That leaves it with 1 1 0 1 0 1 0 1. It adds the ones together. 1 2 3 4 5. Let's look at here. 1 2 3 4 5. Ignoring the start and stop bit. That's 5. That's an odd number, so the data is correct, even though we know it's not, because we can see that 2 data bits have been corrupted. An even number of corrupt bits meant that the error went undetected. There needed to be a more reliable error checking method. Fortunately, 2 methods have been developed. These are called checksum and cyclic redundancy check. These more reliable methods are used for communications these days where the data packet consists of more than just one character of data, taking up usually 10 bits. The ASCII code, the parity bit, the start bit, and the stop bit. So before going into these newer error detection methods, let's look at a typical data packet these days. So here's my data packet. It consists of a number of things. Now this is very basic, but it's all you need for the HSC. So there's a start of header which alerts the incoming computer that this is a new block of data or a new data packet. There's the IP address of the receiver. Now I've written it as a 172.20 and so on. In reality, it'd be written as a bunch of ones and zeros. There's a packet number. If I'm reading this in binary, that's 3, so it's the third packet that's being sent. There's a block of data. Now this block of data is usually between 1,000 and 1,500 bytes in length. There's a spare speech bubble, which shouldn't really be there. There's the sender's IP address, and again this would in reality be in binary. And there's the checksum or the CRC, the error checking code, which is added on to the end. So that's what my data packet will look like. Now how checksum works. Okay, so if we focus on the data part of the packet, the data in the packet is typically up to about 1,500 bytes in length. In checksum, the data is treated as a bunch of bytes. So if we take a look at the diagram below, you can see that our data has been broken up into a whole bunch of bytes, each being 8 bits in length. The bytes are added together, so we have a sum like this, where I'm adding the bytes together from the first byte right through to the last byte. The result is called a checksum. That result of the calculation, the checksum, is added to the end of the packet and it is sent off to the receiver. The receiving computer performs the same calculation. If the checksums at the sending and receiving end are the same, the data block's determined to be accurate. In some instances, an error can occur. In this case, I've had a 0, it's been changed into a 1. The checksums, when added together, will give different numbers because we're adding a whole bunch of bytes, but one of them has got a different number in it, so the results are going to be different and the error will be detected. Now the chances of multiple errors occurring, which result in exactly the same checksum being produced, is very small. This is one reason why checksum is preferred to parity bit approach to error checking, because the chances of an error being missed is very small. Now in cyclic redundancy check, the data is treated as one long number. So here we have our data. Now this time it's treated as one incredibly long number. The long number is divided by a agreed upon number. Let's say it's 23. So we have this division sum taking place. Now the result of that is 433,023, remainder 17. It's the remainder that's the important part of this. Again, here is our block of data. The remainder of the calculation, the CRC, is included in the packet in binary form. 17 in binary is this number, that's why that's the number that I put in there. The remainder of the calculation is added to the data packet, gets sent. The receiving computer performs the same calculation. If the cyclic redundancy checks are the same at the sending and the receiving end, the data block is determined to be accurate. Again, if an error occurs, the CRCs will have different remainders and an error will be detected. The chances of multiple errors occurring, which result in exactly the same CRC being produced, is very small. This is a reason why CRC is also preferred to parity bit approach to error checking. Now here's some bonus knowledge that might help you because it could come up in a HSC question. In the good old days of the 1980s, data transmission was slow. In fact, it was very slow. Data packets all contained the information people wanted to send or receive, but the packets also contained a lot of other data called data overheads, which ensured accurate communication and ensured communication could take place at all. In the case of parity checking, the data overheads made up 30% of each packet. So here's my packet. I have my 7-bit ASCII code, and that's the data. And I have 3 pieces of data, which are the overheads. The start bit, the parity bit, and the stop bit. They're not part of the actual data itself, but they are needed to ensure that the message gets through. And that's 30% of this data packet. So that's quite a lot of data overhead. Now, if we take a look at a data packet that is used in CRC or checksum type approaches, you can see that I have a huge amount of data, and the overheads include the start of header, the receiver's address where the block is going to, the data packet number, the sender's address where the packet's coming from, and the checksum or CRC which gets added to the end. They're all added on to make sure that the communication occurs effectively and accurately. They're not part of the data itself. However, because the data block itself is so big, it means that the data overheads are closer to around 1% of the entire package. Now that's heaps better than when parity checking is used, because in the transmission method that uses parity checking, we have 30% overheads. In this transmission method with these data blocks, we only have about 1% or even less data overheads. Alright guys, I hope that makes sense, and I'll talk to you in class. What you need to do now is go ahead and do the associated work.